Hey troops, I wanted to talk about waves here. You're familiar with ocean waves. We have talked about light waves and radio waves, X-ray waves, all kind of electromagnetic radiation. There are basically three kinds of waves here that I want you to think about, and those simply are mechanical waves, electromagnetic waves, and there's this weird one that we don't really need to know about, but I'm going to throw it in here anyway, matter waves. Let's talk about the mechanical waves first. Right there, you're transmitting energy through some kind of medium. And there's a bunch of examples up there. Water waves, so like an ocean wave. There's the medium. The water is the medium. It's the material that carries that energy. An earthquake, the ground would carry vibration through it and be a mechanical wave. If you pluck a guitar string, sound waves propagating through the air is a medium and it carries that energy as it packs, as there's pressure, high pressure and low pressure regions. Those can be either transverse or longitudinal waves. I'm going to show you that in just a second, but those are all mechanical waves. We've already talked about electromagnetic waves, where you have light, X-ray, infrared, radio, all of those. They carry energy as well, but you don't have to have a medium. It works in a medium. Of course, you can shine a light through the air in your room, right? But it can also go through the vacuum of space. So there doesn't have to be a medium there, or if there is some kind of medium, we don't know about it. They tried to find one a long time ago. I told you about that. Couldn't find it. Doesn't mean it's not there. It could have just been looking in the wrong way, but as far as we know, there's no medium there that has to carry electromagnetic waves. This last one, the matter waves, very weird, very strange. Electrons, the particles, have wave properties. Protons have wave properties. A baseball would have wave properties, but it's very, very small. And the larger the object gets, then the smaller those are. It's weird, okay? You don't really need to worry about that. But the idea is that electrons can kind of spread out around the atom in wave-like properties, and that's enough to say about that. If you want to look it up. Matter waves would be a good place to start. Not what we're talking about. I'm interested in the mechanical waves and the electromagnetic waves. I mentioned transverse versus longitudinal waves up there. And so here's one image of how that would work. A longitudinal wave goes along the wave, so you have high pressure, high compaction regions here, and emptier compaction. If you pick a particular point like that red point right there, you can see that it's vibrating back and forth. Maybe the easiest way to set one of these up would be to take a spring or a slinky, lay it out on a table, and then pull some of it, anchor it at both ends, right? So I've got this thing suspended between 2 points, and I'm going to reach up there and grab some of those coils of the spring and draw them back towards me and turn loose. And you can see how those yellow spring coils would go towards the wall, hit, bounce, and come back, and that vibration would just be continued through there. So that's a longitudinal wave. The other one at the bottom there, the transverse wave, is more like an ocean wave. The medium is going up and down. The ocean is going up and down. If I put a little red rubber ducky in the ocean wave, the thing would rise and fall with the wave there. It would float up on top of that wave, and as the wave passed under it, it would go back down like that. So that's the difference there. The medium is either moving in the same direction as the propagation of the wave, or it's transverse. It's perpendicular to the direction of the wave. The wave moves to the right and in the X direction, and the red dot, or any dot on here, moves in the Y direction. Here's one more image of that may help a little bit more thinking about individual particles there. You can see that red spring on the longitudinal wave, and the actual coils, the actual atoms, whatever you want to think about, they are moving in the same direction, and they're both in the X direction. Whereas with the transverse wave, the wave is propagating to the right, and you can kind of follow that here, hit that peak, and it just goes all the way down to the end. But the individual atoms or the individual molecules, the medium is going up and down. So that's what we're talking about. Again, any kind of mechanical wave could have either this or this, but you know, and like an earthquake actually has both. It has a longitudinal wave that we call the P wave, and then there's a transverse wave that's the S wave, the secondary, primary, and secondary wave. So, but that's a discussion for another day. Got some terms, definitions here you need to know about waves. First up there is the amplitude. The amplitude is the height of the wave, and we always measure from the center line right there. So from the center line up to the top would be the amplitude. It'd be that same distance from the center line down to the bottom. So you could measure either one you want. But if that amplitude is A, the symbol for it is A, then let's say A equals 4. It's going to start here at 0, go up to positive 4, back to 0, down to negative 4, 0, 4, 0, negative 4. Just keep doing that forever. So it's that limit on how high the wave goes. I've got a number called the wavelength. We use lambda for that, the Greek letter lambda right there. And that is the physical distance it takes for that one wave occupies. So here from the top of this wave to the top of the next wave, if I got my measuring tape out and measured that, that would be the wavelength. Probably measure that in meters, but inches and feet and miles, whatever else would work too, but meters would be our favorite one. You could also start here at where it crosses the axis and goes all the way up, all the way down and back, and now it's ready to do the whole thing again, all the way up, down, back. All right, so it's one complete cycle. It is the distance. The wavelength is the distance that it takes for one wave that it fills up. I've got a velocity of propagation. How fast is the wave moving? We'll say to the right here. That's given by V, and there is a little formula here, the frequency times the wavelength. I haven't told you about the frequency yet, but the frequency is how many times per second that wave passes. So if we were to go back to this one, I'm going to try this. I don't know if this is a good idea or not, but right here I'm going to count 1, 2, 3, and if you had a timer going, you could work out how many waves there were per second. Well, if you count cycles per second, we also call that unit hertz, then that would be the frequency. And anytime I take the frequency and multiply by the wavelength, then I get the velocity of the wave. That makes sense, right? If I have number per second, and this is in meters, and I put those two together, then I'd have meters per second, which would be a velocity. So that works out kind of nice. Over here I've got an expression. We've talked about the frequency. I've got this other number called the period. The period is how long it takes, the number of seconds it takes to make one wave, one cycle right there. So you can see why the frequency is 1 over the period. If it takes 2 seconds to go from here to there, 2 seconds of time, then my frequency is going to be 1 over that, or 1/2 of a hertz. That is another way to say that if I have 2 seconds, a 2-second period, if it takes 2 seconds for that wave to pass, then I get 1 cycle every ½ second. Okay? So those are just inverses of each other. All right? Anyway, those are the terms there that we want to talk about. And you can see that this is a sine wave, right? It starts at 0, goes up, down, and back, right? So that's a sine wave would be an excellent choice there. We could also use a cosine. If I say, well, my y-axis is right here, if I let it start at the top, go all the way to the bottom and all the way back up, that would be a cosine. So it's just kind of up to you, whichever one you use. I'm going to use sine here. That's what your book does. And here's a little math model with all of the terms in there that we've talked about, and a couple that we haven't yet. But right here, A, the amplitude. We know that any kind of sine function is trapped in between -1 and +1. So when I have a sine and I multiply that by some number, this is going to scale it up. So instead of going between 1 and -1, now it's going between A and -A. If A is 6, then this is going to reach a peak of +6 and go down to -6, oscillating through 0 every time. A is the amplitude. K is what we call the wave number. It's the number of radians per minute. I'm sorry, per meter. And you can see that that number appears right here in front of the x. I need to have a function that has x and t. You can see that this is giving me y, the height of the wave at a position at a time. It makes a difference how far out here I go, what the height of the wave is, and it also matters what time it is, because right here it's at a maximum, here it's at a 0, with my little crosshair, minimum, 0. So if I wait long enough, it's going to go through the whole cycle, or if I move left or right, it's going to go through the whole cycle. And so I need to know x, I need to know t, but then I need to know a number that says, well, how fast is it going? Is it taking the cycle in the x direction? How long? How much time does it take to go through a whole cycle? There's one other number here called phi. That is the phase shift, and the phase shift is how far away we shift the beginning of this thing. I didn't put a picture of that up here. This one's not usually terribly important, but let me just draw a little wave here. Like, see, that's a crummy picture, but whatever. If I draw a sine wave that looks like that, then I could shift the whole thing to the left or the right, like that, and we could talk about that phase angle right there, how far the whole thing was shifted to the right. Okay, so that's all that a phase angle is. All right. I got a little example here. I've got that math model up top in the gray box, but right below it, it says, if you've got this function, it says 1.2 sine 4x minus 2t plus 1.3, and the units are in there as well. I didn't mention those, but they want us to find a. That's easy. A is right there, 1.2. They want us to find k. How many waves per meter? Okay, well, k is this number right in front of x. There's x, so it must be 4 radians per meter would be what they'd want right there. Omega, how many waves per second? There's omega. I've got a 2. Notice that the negative sign is part of the formula, so I just put a +2 there for omega, like that. Last one on the left is phi, the phase shift. That's over here. It's 1.3. Big deal, right? You just write down those 4 numbers. They could also ask for lambda, the wavelength. And you remember that the length of the wave is tied up with this number k right there. So if I take 2 pi over k, then I'll have the wavelength. And since I know that the k was 4, I could just come in here and say 2 pi divided by k, which was 4, and that would be my lambda. Each of these waves would be 1.57 meters long. They might want to know the period of the wave, how long it takes, how many seconds it takes for each wave. I need to take 2 pi over omega. Remember, this number says how fast is the wave going in time, how fast does it wiggle, and I need to take 2 pi, that would be 1 complete cycle, right, divided by omega, which was 2, and I'm just going to get pi. 3.14 seconds would be the time it would take to do it. One last one here, the speed of the wave. How fast would this wave be moving to the right, or whichever direction it's going? I can either take lambda over the period, the wavelength over the period, or I can take that angular frequency over the wave number, omega over k. So either way should work fine. I know that omega is 2 and that k is 4. 2 over 4 is 1/2. All right, so it's going to be moving at 0.5 meter per second. You can see that, that lambda, remember way back there we said that somewhere I had it's just there. Okay, 2 pi over lambda, 2 pi over t. So basically, if I'm taking lambda is 2 pi over k, so if I put that in, and the period is 2 pi over omega, if I stack those up, the 2 pi's are going to cancel. I got to invert and multiply. I get w over k, omega over k, right? All right, so big deal. Write down all of those you know, connections where lambda equals 2 pi over k. Have those on your card. Have what all these mean, and then, you know, if they ask you, well, what's the wave number, you know, you can come in here and say, okay, it's just that number. Big deal. All right, but you do have to kind of know which one's which. Right here, using that same model, y equals some number times the sine of all that stuff in the parentheses. Those of you that have had 10 cents worth of calculus know that if you take the derivative of the position, you get the velocity. So if you haven't had calculus, you don't need to worry about it. But right here, I could get the velocity is negative a omega cosine of all that stuff in the parentheses. That doesn't change. When you take the derivative of sine, it goes to negative cosine. And then I got to reach in here, and since I'm taking the derivative with respect to time, I'd have to pick up an omega and put it out here. All right. So that would be what we have there. We could also write that as the amplitude times the frequency would give me the velocity, the maximum velocity. Amplitude's the maximum height, and I multiply that by the frequency, then I get the maximum velocity. So if you want to cook it down to that, that would be fine too. Okay, if I take the derivative one more time, I'd get the acceleration. And again, it's going to be a function of x and t. I have to know where I am on the x-axis and how long it's been since this wave started wiggling. Both x and t are important, but I'd take the derivative again. Cosine goes to sine. I get an extra omega. It comes out here. It's still negative. Right there's an expression. So that's kind of neat. You pick any point. Right here, they pick that red one. Okay? So I'm thinking about that red dot, and it's moving up and down. The first equation here tells you how high up or down above the line it's going to be. It gives me the y value. The second one says how fast is that dot moving at any particular time. When it gets to the top, it has to stop and go back the other direction. When it gets to the bottom, it stops. When it goes through the middle, it's going as fast as it ever did, right? That's the maximum speed at the center line right there. So that's always changing in time and position. The acceleration, how fast is that red dot speeding up or slowing down? When it gets to the top, it has to slow down. So the acceleration goes up, stops, right, goes the other way. That would be the maximum at the edges, the top and the bottom for the acceleration, the minimum for the velocity. So anyway, that would be what they'd want you to do there. I would write down this equation, y. I'd write the v down. I'd probably put this one right here, you know. And for a, I'd write that one down. I don't know that I'd put the Umax and AY. It wouldn't hurt, but, you know, whatever. Okay. Did you know you can have two waves in the same place at the same time? We can add waves together. This is called superposition. We've used that word before. It meant take the effect of each piece and put it together. And that's all we're doing here. You're taking two waves and you're putting them together. What's the effect of the first wave, second wave? Add them together. So in the animation here, you see that there's one wave that's just kind of static there. It's a standing wave, I guess you could call that. And then the second wave is moving at a different frequency. So it's moving to the right. But if I take this wave and add them together, then I get that dark blue wave there. And you can see that it's sometimes when these things reach a high and low spot, it goes to 0. And when they both are high, then it would add up to a maximum there. So I'm adding those two waves and seeing what they add up to. Over here on the right, I have two waves, a red wave and a blue wave, and they're passing through each other. They're occupying the same space, but that black line is giving me the sum of those things. Now you can kind of do this on your calculator. Let me just kind of show you. I think I've done this before for you, but if I came in here and put down a couple functions, let's say the first wave is just sine of x, like that. And I put in a second wave, and here we'll say if cosine of x. There is a way to come in here and to, I'm going to get out of this, quit mode. Tell you what, actually I'm going to graph those two for you right there. And that's not what I want. Hit the graph. Okay, there's the, that's the sine wave. And then the cosine wave is right there. And we'd like to know what those are when you add them together. And you can kind of do this by hand. You can see that this one's 1. And then right there's a 0, and 1 plus 0 is 1, right? Right here I've got a 1 and a 0. That's not very interesting. So, you know, it's kind of hard to see what that's going to be. If you hit this variable button right here and go over to Y variables, and you want function, then you can say Y1. Oh, you know what? I left out one thing. I'm sorry. Hit the Y equals button. Go down here, and we want to graph what happens when you add those two functions. So I'm going to hit variables, slip over to Y variables, function, and I'm going to take Y1, and then I want to add to that variables, Y variables, function, and go down and get Y2. So now it's going to take Y1, which was sine, Y2, which is cosine, and add those two. And when I graph that, I'm going to get a third line. This is going to draw all three. We've already seen what Y1 and Y2 are. So I'm going to go over here, and I'm going to turn this one off, and I'm going to turn this one off. All it's going to graph is one graph now, which is going to be the sum of those two. So these are kind of easy to do on your calculator like that. But here you see that we get kind of a different wave. It's not the same as you know, it's the sum of those two, and that'll do it. If you come in here and change, let's make this 2x right there. That's going to make it oscillate faster, right? That's kind of like that wave number that we had. So see how you can get all sorts of strange things. Maybe one of them, oh, okay, well, since I changed it, it graphed it, I'm sorry. Yeah, so that actually graphed two lines there. It graphed the first one and the second one. Take that back off. I'll come down here. Maybe this is, we'll change the amplitude of this, put a 4 cosine. I don't need to see that graph like that when I hit graph. You know, so that's the sum of those two waves. You can buy noise cancellation headphones, which take the incoming sound, the ambient sound around you, whatever's going on in the room. Let's say you're a pilot or you drive a lawnmower or something all day. All that loud noise will damage your hearing. So what they can do is they can take that sound wave and they can invert it. Say, I want to see what, you know, if I've got that 4 cosine x and I take negative 4 cosine x and I add those two together, then you know, what's my wave going to look like? It's right down the middle. I inverted the wave, added it to the original wave, and the two cancel each other out, and I don't get a you know, all that noise in my ear and all that damage. So there's some practical purposes for all this. Sometimes sound engineering, you know, they'll invert the sound or something. Anyway, need to say something about wave reflection. What happens when a wave hits a boundary? Right here you see there's a pulse wave coming like this, and it's going to hit this wall, but it's rigidly tied in. When that one hits, it's going to invert and go down. It's going to return on the inverse side. It inverts that wave, flips it upside down when it hits. So it's traveling to the right, inverts, comes back on the left. The little pink animation here is trying to do that for us. Bloop, and it's going to flip and go to the other side. On the other hand, if it's not fixed, if it's loose over here, a free end, like I've got a little loop tied around a pole, as that pulse comes to the right, it's going to take that loose end up and back down, and it's going to return the pulse on the same side. that you had. You can see that animation down here trying to show that. So bloop, and it's so those are kind of the differences there. The last slide here is about standing waves. What happens when I add two waves that are the same, have a lot of those same wave numbers the same, and so you end up with what's called a standing wave. In the animation here, you've got a green wave, which you'll notice is moving to the left. You've got a blue wave, which is moving to the right. They're passing through each other. Sometimes they cancel out, sometimes they add up, but because they have the same frequency, same wavelength, same period, same wave number, all of that stuff, however you want to say it, then I get that black line is the sum of those waves. And you can see that it's just going up and down and up. It's not, the black wave is not moving left or right. It's a standing wave. It just stays right where you put it. In the picture in your book down here, they took a bowl of milk and put it on a room fan, a box fan, turned the fan on, and the vibration of the fan set up this standing wave that would be, you know, like all that vibration of the waves coming together, and the milk just kind of goes up and down, and you can see the rings right there making a little standing wave. Some terms that we use when we're thinking about standing waves, and a guitar string is a good example here. If I take a string and stretch it off between 2 points, tie it off, it's some length right there. If I pluck the guitar string and it's making this up, down, you know, we said that it flips when it hits that solid boundary of the nut. It's going to go down, up, and then invert and come back, and it's just going to oscillate like that. That would be n equals 1. I've got one, you know, standing wave there. And what I notice is that's only half of a wave. So half of the wavelength is the length of the string. If I multiply both sides by 2, then I'd get that the wavelength of the full wave is twice the length. So I'd have to go all the way up, all the way down, back to get a full wave. I've only got half of a wave here. In this one, where n equals 2, I've got a standing wave here. I got a second standing wave there, so there's 2 of these. And you can see that that is a full wave. It goes all the way to the top, all the way to the bottom and back. So that's a full wave. The wavelength is the length of the string. And so we've just got that. What if I had 3 standing waves? These are called harmonics. And they're important in playing guitar and piano and other stringed instruments, as well as, you know, wind instruments as well. But you've got 1, 2, 3 here. A full wave would only be this. So in the length of the string, I've actually got 3 halves, 1.5 full waves. And so lambda over 3 is 2/3 L. And you can see that they're building a little pattern over here. 2 over 1, 2 over 2, 2 over 3, 2 over 4. And generalizing that, the wavelength is going to be 2L over N, N being the number of harmonics in there. Right here, I've also got the frequency for each of these, and N is that number of harmonics again, the velocity of the wave divided by 2L, and they kind of do this little thing. Remember that velocity was frequency times the wavelength, so if I've got frequency divided by the length of the string, then that's going to work out to the frequency there, and so I could do that either way. And you know, whatever number you need to put in for N, those are down here, but just building up some patterns with that. All right, so that's waves, and there are a lot of variables and ways to get from, you know, lambda to K and F to T, and you got to know all those and stuff. But once you've got those written down, then the main thing is just putting in these numbers here. And if I just take this right here over, and we do like a little example real quick. Get that on the screen, make it fit. Come on. All right, sweet. Put that right there. Okay, so just to show you punching one of these into the calculator, a problem might say, here's some numbers. Let's say that the amplitude of the wave is 7. The wave number K is, I don't know, 0.3, and omega is 2, and the phase shift is 1.7, whatever, like that. Okay, and then they might say find y at a position, x equals 3.3 meters. So, I'm thinking about this thing going up and down. Sine's going to start right here and go like that. This one does have a phase shift, so that is going to move it back a little bit. But I want to come 3.3 meters over here. And then I also need to know the time, because at that point this thing is rising and falling all the time. So they'd have to give me time equals 6.8 seconds. All right? And then it's just a matter of putting in the time. Here's my function. So I'd have 7 times the sine of 0.3 times x was 3.3 minus omega. That's 2. I got the time is 6.8. I'm leaving out all the units here. Remember, they all canceled out anyway. But that would be what I'd want to put into my calculator. If you want to see the units, this was radians per meter, and this would be in meters. So the meters cancel out, and I've got radians, and I can take the sine of that. This one would be radians per second, and this would be in seconds, so they cancel out, and I got radians. And, of course, this one would be radians as well. So just trying to take the sine of an angle there. And I grab my calculator. I'm not sure I emphasized this enough. I said it on that slide, I'm pretty sure. Calculator needs to be in radians. Anytime you see these 2 pi's, you're talking about radians there. So I'm going to pull over my calculator, and I'm going to hit the mode button just to make sure that I'm in radians, and it is. But if it wasn't, then for this test, we'd want to move it over to that. Anyway, here's what I'm trying to put in. 7 sine 0.3 times, just make it look just like it does. And it's going to give you a value that says here's how high above or below the line it is. We know the amplitude's 7, so it's got to be somewhere between 7 and -7. This one's almost right there at the top, 6.97. If I change the time just a little bit, and remember my time was 6.8, so let's go to 7.2, something like that. A little bit later on, I'm guessing it went all the way to the top and came back down. If I wanted to know, though, I'd have to go find the velocity. If the velocity were positive, that point would be still headed up. If it's negative, it's going down, right? So you could tell, I know I'm close to the top of the wave with this one, but am I going up or am I going down? You could crank out the velocity right there and see. Okay? The acceleration would also tell you. So, well, maybe not. Velocity would be better. All right. Anyway, that's wave stuff. Let me know if you have any questions, and we'll figure them out. Thanks so much. Have a good day.